Okay, I think we can start. I'm sorry for being late. What I suggest is that we distribute the sheet after the break, or at the break, because it will actually refer to the topics that we want to treat today. So to start with, I would like to, as usual, recall what we did already last time, to get this overview of an overview. At the moment we are still in the process of reviewing the lecture on optimization, but still it's good to keep the main messages. And what we have learned last time, which I would like you to remember, is that the student type optimization methods very often approximate the true KKT matrix with an approximate KKT matrix which has some matrix B here, which is in most general form depends on the iteration, and then here we have the derivatives of all the constraints at the current iteration, and here the dg by dw wk transpose, and here is 0. So this is the general form of approximation, and in particular if this approximation depends on the point at which we are, which it does, for example, for Gauss-Newton methods, then one criterion which helps us to, which is a tight criterion that helps us to understand when this thing will converge and when it will not converge locally, is given by the criterion where we have just Z transpose B, and B is now a function of all the variables Z, at the solution Z being primal and dual variables, so this could be all B of zk, so this could be the form that we are interested in now, where this matrix is approximated. And if this matrix is actually bigger than half the reduced exact Hessian of the Lagrangian at the solution point, if this criterion is satisfied, then we have a chance that it will locally converge, and otherwise not. Yeah, so not we have a chance, but in this case it will locally converge in the neighborhood of the solution. So that was the thing that we have derived last time, and please note the factor 1/2. So roughly speaking, you can be 1/2 too small with your Hessian approximation. You can be far too big. It will not be very fast, but it will still be local convergence if you have it very big. So to be on the safe side, rather choose the Hessian with larger rather than smaller. I think this is the main messages from last time. Please also keep in mind that the Gauss-Newton method is something you can apply if you have least squares objectives, and very often it's a very useful one. So we should keep in mind that this is a method to be used if possible. So we want to continue with new topics now, and we didn't answer one important question yet, and that is how to address inequality constraint problems. So once you have inequalities in your problem, things will change a bit. But fortunately, Newton type will also be the answer here, and we will see that all these ideas can be generalized easily. So this is section 4.3 about inequality constraint optimization. And of course, the problem setup I don't need to write down again and again, so you know what I mean. But what I can write down again is the KKT conditions in the more general case. And you remember them? They were that the Lagrange gradient at Z, maybe I distinguish it between lambda and mu, should be equal to 0, that the equalities should be equal to 0, and I omit all indices. Of course, it should be at the solution, right? And then that the inequalities should be, and I write it like this, should be smaller than 0, h of w, and they should be orthogonal to the multipliers, which should be bigger than 0. So that's the last condition, this complementarity condition. And if you look at it, it's making sure that the h is smaller than 0 and the mu is bigger than 0, and the product of both is 0. So if you depict it as a set in two axes, in one axis, and I think I want to do it like in the script so that we have the right, yeah, exactly. So we have hi, and here's hi of w, and here is mu I, so two axes. And if you think of it, what it means for each component, it means that the mu I should be positive, that the hi should be negative, and the product of two should be 0, so we are actually allowed to move only on this set. So this L-shaped, okay, it's an inverted L, a mirror L, but I call it still L-shaped set. And this set is, of course, as I said already, the source of all difficulty in inequality constraint optimization. And you know that Newton's method is good when you have differentiable functions, but this is not differentiable. It's a severe nonlinearity that will make Newton's life very difficult. But there's different ways to deal with that. And one way, which is quite elegant and also very successful in practice, which I will therefore continue start with, are the so-called interior point methods. And interior point methods start with a very simple idea. The idea is just to say, if all this constraint here is so difficult, why don't we replace it by something nice and smooth and differentiable, which looks similar but is not identical? And so you choose something that's similar, for example, a set that looks like this. Yeah, so you curve it. And of course, this is a bad approximation and it might not be a perfect approximation, but then the second idea is that you choose such an approximation class, so you make it from very bad but quite smooth to a better and better approximation that gets less and less smooth. And in order to do so, you will actually relax or change, modify this complementarity condition or these complementarity conditions by a different system, and I will easily write it down. So the system will be, here's the gradient with respect to W, of course. W lambda mu, G of W equals 0, so equals 0, equals 0. And now, these sets are easily described by hyperbolas, which say that the product of mu and h should be equal to a value that is in this case negative, because that's on the negative quadrant. So we basically say that mu I times hi of w should be equal to minus tau, or we also put the tau here on that side, and then we have it here. And so tau, if tau is bigger, so this will be a big tau, and this will be a small tau. And that corresponds to the solution set of this system of equations. So you see that it's this system that you want to solve for a decreasing sequence of tau. So that's already the idea. So you see, okay, this is a root finding problem. It's something that you could just call, if you think of it, it's an R of some Z. Actually, it's the same space that we had before, W lambda and mu. But it now also depends on some other variable tau, which you will reduce during your iterations from a very big value to a small value. So that's a very intuitive idea, and it's nice to look at it. There's some things I want to note, which you should know about it. The first thing is, if you think of the solution set that I described here with the fixed tau in the space of mu and hi, it's not only comprising these branches, but it will also comprise this branch, right, on the other side. So because here would be the product is positive, so that's not possible, and here it's also positive, but here you also have a product that's minus tau. And so these would be the shadow solutions, and you somehow need to avoid them. You see that this and this branch is disconnected, so you can hope that if your Newton's method is here, that if you are not having extremely bad luck, that you don't jump to that side, right? But you will actually ensure that your steps will never leave this region, this quadrant, by making them shorter if necessary. Yeah? So this is just already the intuition here, but this is one remark I wanted to make. The other is, and that is maybe more important in this context, is that one can actually looking at this gradient here. So what is this Lagrange gradient? It is actually the gradient of the objective plus the gradient of the constraints times lambda plus the gradient of the multipliers, and I put now a sum here to make it explicit times mu I. So you see that it contains terms here that are a gradient of hi times mu I, a bit like these terms, but what I could do is I could try to replace the mu I from this equation, and then if I replace this equation here, then the mu I could be written as minus tau divided by hi, right? So then I would get this whole thing here, minus, and I just said there would be a tau, and the sum of hi, and now it's over hi. Yeah? So you see what I just did, I replace it here. And so now you realize that what we have here is can be seen as the gradient of a function that I could call f tau, I give it this name, plus nabla g lambda. So I could actually summarize these terms and these terms together by defining a function f tau, and maybe I directly state the problem. So it's equivalent to, for solving the following problem, where I minimize over w not only the objective function but also the sum, and I multiply it with a tau, the sum of all the inequalities, but each weighted with a logarithm. So I from 1 to nh. And then the only remaining constraints would be the equality constraints. So this would be a problem which I could set up and solve. And I think I'm wrong here because there's a minus sign missing. Here needs to be a minus sign. And if I differentiate that function here, what would be the derivative of that? It's actually the outer derivative is, so minus tau log minus h. So what is the derivative d by dw of this thing? It will be minus tau, then divided by minus h for the outer derivative, and then the inner derivative is minus nabla h. So, of course, I put the transpose here to get the gradient. So then you see that this is actually equal to minus tau times nabla h divided by h. Everything with an I. So indeed, if I take this objective function, so I could call this objective function f tau of w, and it's an objective function which contains both the objective and a penalty that penalizes coming too close to the boundaries of your constraints. So I would like to give the second interpretation, which is actually this root finding problem is equivalent. If you have a solution to this one, you also have a solution to this one, where the mu's are just not present, right? So the mu's you can always get by inverting this equation to mu, if you would have solved this one. So this one we call the primal dual formulation, if you solve that, primal dual, and this would be the primal formulation, or the primal IP method, if you just address that one. In practice, you usually prefer to address this system directly, but I like this one because it gives you some interpretation in addition to this rather abstract motivation where you just say, oh, I smooth these non-smooth conditions, because it also tells you what you really do on the terms of the objective function. So for the objective function, what you do is you add these minus tau times the logarithm of minus h. So what is this function? So let me just plot as a function of hi, which is a bit, hi. Hi is the axis which should be negative. So what is minus tau log of minus hi? I put it as if it would be the input. It's a function that is, it's only defined if the hi is negative, otherwise the logarithm isn't defined, so it must be living here. The logarithm of something negative, positive, is a number that goes like this, right? But now I put it with minus tau, so it will be actually inverted, so it will be looking like that. So that's the logarithm, but in this particular way of scaling. So what you see is it goes to infinity here. So to infinity here, and it goes to actually minus infinity here. But it goes very flat to minus infinity. What is interesting is that it pushes you away from the boundary of the feasible set, because here's the boundary to being feasible, and it will never allow you to move there. And if you make your tau smaller, then of course this whole thing will be multiplied with a small factor. This point will not change, but everything else will be contracted. So it will more and more approximate a cost function which is 0 for everything that's feasible and infinity for everything that's getting infeasible. So it gives you a very intuitive idea why these things are called interior point methods. This barrier term, yeah, it's called a barrier, minus tau log minus hi, pushes solutions inside into the interior of the feasible set. So that's main point to keep in mind here. And so now, of course, there is some technical questions. So I just said solve it for a decreasing sequence of tau. So there are different strategies of how to adapt this tau. Usually, as I said, you start with a very large value of tau. You solve such a system with a normal Newton-type method. Once you have solved it, you reduce your value of tau, and you start the iterations for the next one at the solution guess that you have found with the last value of tau. Yeah? So you actually use what we call a homotopy or warm start. Yeah, warm start and homotopy. Oh, it's actually the same in this context for decreasing tau. And you know, and you remember, Newton's method performs very well if you start close to a solution. So if you don't change your tau too much from one solution to the next, you expect very fast quadratic convergence. So very often people use exact Hessians here. So usually use exact Newton. But that's of course not necessary all the time, but preferably you use exact Newton. So I think here we had a nice visualization of the complete picture. This is just a term that you add as a penalty. If you want now to look at this function f, w minus tau logarithm of minus h of w for one constraint, and for example my cost function f is something simple quadratic, and my bounds are so I have a w element in R. So this is an example. It's actually figure 4.2. I want to explain it. So if you had an original cost function that looked like this, for example, yeah, so in one variable, this is w, and then you have two bounds, and one of the bounds says that you should be above 0, and the other says you should be below 1. Yeah? So you have actually 0 smaller than w smaller than 1. Then for a high barrier parameter, your cost function will look like that. And for a very small one, it will look like that. So it's nearly the original problem, as you see, but it has now the bounds as some in a smooth form. It incorporates all the bounds in your objective. So it's a very intuitive way to deal with this non-smoothness. And you see, of course, that it's getting more and more nonlinear at these points, the smaller your tau gets, and that's why it's so important to do this homotopy, because you wouldn't be able to solve the problem with a small tau without a good initial guess. But once you're, so to say, your solutions this will be the solution to this problem, and then this will be the solution to that problem, and step by step you will actually follow these solutions and always initialize the Newton's method very close to where you are, so it will not get out of the area of local convergence. So that's something about the motivation. And maybe one thing I should say is that the convergence of your objective value, yeah, so the objective value that you get as a function of tau, minus the absolute optimal solution is of the order of tau. So if you have the tau very small, then you're also very close with your objective to the real objective, depending on the dimensions of your problem and so on. So this is just, you see that the objective values really converge linearly with tau, the height of the objective. Okay. So for the implementation, I wanted to say a few words. So the first one is that if you want to implement these methods, you see already that it's a bit tedious that your inequality constraints, which are nonlinear functions of your variables, that you want to keep them always in the positive or on this orthant, and I said to you, you want to be on this left upper orthant all the time. So you can only ensure that for things you have under direct control, but the function h of w you don't have under direct control because it's a nonlinear function. So even if you make your step a bit shorter, you might not be sure that the h of w is still in this right orthant. So for this reason, in practice, you implement always something where you introduce a slack variable for the h. And so it will look like the following. So you will actually add a si, which you can interpret with being minus hi of w. So that's basically what you want to introduce. And then you augment your equation system by this. So you have the gradient here, w lambda mu equals 0, g of w equals 0. And then you have these, this condition here, which just says hw plus s equals 0. And your last condition is then that the mu I times the si, and now I need a minus sign here, minus tau equals 0 for I from 1 to nh. So this is a new system of equations. It's a bit larger, if you see, but it's still a square system of equations. How many variables does it have now? It has the w, it has the lambda, it has the mu, and it has the s. So it has actually, if you think of it, it has n for the w, plus ng for the multipliers of the equalities, and then plus 2 times nh variables. But it also has the corresponding number of equations, namely here n, ng, nh, and another nh equations. Yeah, so it's from the dimension still a square system. Augment with what we call slack variables. And these slack variables allow you to always stay in the positive orthant by making your step shorter. Yeah? Because if you are in the positive orthant, I mean, now my plot that I had before is actually reversed. So I have the mu I here, and here is now the si, and now I want to be on the positive side of this orthant. That's just due to the sign change. So this is where I want to be. I will be usually somewhere in the neighborhood, at least, of this orthant. When I linearize the system in Newton's method, and linearization basically means it has a tangential approximation of this whole set. And so when you do your step and you realize that your step is getting you, the full Newton step would get you here, for example, you will simply not do the full Newton step, but you will stop slightly shorter than just before you touch this boundary. And you can very easily compute these numbers analytically, even once you have your step. So you have a very easy way to make your steps shorter. So shorten the steps to always stay in the positive orthant. To always stay in positive orthant. Now we call this the positive orthant. And another thing that I should also say is you don't care anymore about having a feasible initial guess, because you could just choose any w. Yeah? Of course, this will not be optimal, so it will not have this satisfied, it will not have this satisfied. And this one might also not be satisfied, but you really make sure that the s is positive and that the mu is positive in your initial guess. So you will not care about this being truly a feasible point with respect to the inequalities. Yeah? So this is one thing, and the other thing is can start infeasible. In W, of course, all right? So you shouldn't start on any point that's positive. I mean, this mu I should be positive and the Si should be positive in the initial guess, but everything else can be infeasible and suboptimal, and that's a big freedom for your interior point method. And what I just sketched, yeah? So this method that I just sketched, which uses these slack variables and so on, that's the method, okay, it's many, many details. That's implemented in the solver IPOpt that we will use in many of the exercises, and that is very widespread. So software is, and I think it's good to really advertise it, it's an open source solver. It's interfaced to a lot of tools, including Casadi, and it's quite reliable and one of the best, even though it's open source, so to say, and no one pays for it. It's one of the best performance and robustness for nonlinear NLPs. So this is actually a nonlinear interior point method. And there is, I mean, this whole thing that I presented, you could specialize if you want to an LP. Yeah, then your functions would just be much simpler, of course, and also these equation systems would look simpler. You could also specialize it to a QP. And if you would do it for a QP or an LP, for a QP, for example, this would be a linear function, because it's the gradient of a quadratic Lagrangian, right? This would be a linear function. This would be a linear function. And this would be the only nonlinearity due to mu times Si. So you see that it's actually very structured if you would have a QP or an LP, the same. And in this case, you would not use IPOpt, but you would use a specialized solver that exploits this structure. Yeah. So for LPs, QPs, and other convex instances, other convex optimization problems, specialized solvers exist. And please note that for these convex problems, these specialized solvers, I mean, that's something that, I mean, they are faster because they exploit the structure, and they are also, okay, also IPOpt would converge to the global solution because there's only one local minimum, right? But they are guaranteed to have a complex, I mean, there's complexity guarantees, so you can even ensure that the solution does not change, that the runtime is bounded by a theoretical upper bound. So specialized solvers with runtime bounds exist. Yeah. So just a side remark. So people were very excited when they found out that you could solve LPs with solvers which have a runtime bound. Because for a while it was not sure if LPs are, so to say, NP-hard problems or not. And yeah, interior point methods proved in both practice and in theory that linear programming is not NP-hard. Because some algorithms that existed before, which I will also present in a minute, they are actually, unfortunately, they have no complexity bound. So they can be exponential in the number of problem data. So this was fast and quick, but I want to go on like that, if that's okay for you. Yeah? Because there is this other class in nonlinear programming with the details, and I want to finish this week actually with the rehearsal of optimization, so that we can really dig into optimal control and the specifics a bit later. So 4.3.2 is another section, and this section is about another class of methods for NLPs, which we call sequential quadratic programming methods. And it's another approach for NLPs. We abbreviate it as SQP. And so if you think of the original problem, okay, which I never stated here, but nearly stated. Maybe I state it now once because it is useful to have it once. So this is the problem we want to solve. Okay, so you could say, maybe if there's all these wonderful specialized solvers for convex problems, and indeed they are actually very, very fast solvers for convex problems, in particular for QPs, maybe I could just linearize it and make it a QP. And you remember, or sometimes people say also quadratize, because you somehow keep a quadratic objective. And so you could actually say, at an iteration, you could just say, I want to solve the linear quadratic version of my problem. And if you remember what we did for equalities, we would just linearize our cost function times w plus then a quadratic term. And here in this quadratic term, we would penalize the difference with respect to the current point. But here we use something that I call BK. Hessian matrix. I forgot the transpose here. And then we had the constraints, and you remember here we had a GW plus DG by DW, WK, times W minus WK equals 0. And we had actually discussed that this, if you put the exact Lagrangian here, the Hessian of the exact, the exact Hessian of the Lagrangian here, in the equality constraint case, that would be equivalent to Newton's method. You remember that. And now you could say, if I have inequalities, why don't I just add my inequalities here as well? I also linearize them. Linearizing is an easy thing. I know how to do it. And then I just impose that they should also be satisfied with inequalities. So I keep the inequalities in the subproblem. And then I have a QP. And this QP is an approximation of my original problem. And so I need to rely on some QP solver, which then deals with this inequality. So somehow I give the difficulty to some other solver, namely to the QP solver. But I basically base everything on the fact that there exist good QP solvers. Yeah. So needs QP solver to deal with the inequalities. And so you could say this is like, that sounds too easy, right? So we invent an algorithm that solves an inequality constraint problem by solving inequality constraint problems. So what did we gain? But what did we gain? These inequality constraint problems are very structured. They are QPs. They are easier. And if we choose these Hessians here to be positive definite matrices or semi-definite matrices, we would even have convex subproblems. So then they would be easy and nice and reliable to solve. So that's the outline of an SQP method is actually to how do I describe the algorithm? It's relatively simple to describe it. You would just start at W0 and with some BW0, right? Yeah. Solve the QP. In a loop, you will actually, you need to linearize all these functions, of course. This is like the computationally possibly very expensive step. Linearize F, G, H. So you sometimes, actually this would be the method where you approximate the Hessian. Yeah? So you would solve the QP. This is the other expensive step. And use the QP solution. Maybe I should say get the solution from this QP would be WK QP and lambda K QP, because you get multipliers for these constraints and you get also multipliers for the inequalities, which many of them might be 0. And then you perform possibly a line search or some other globalization dampen step if necessary. So you dampen the step if necessary. That means you set wk plus 1 equals wk plus some factor possibly times wk qp minus wk. Yeah, so this is the step that the QP solver wanted to do with alpha element in 0, 1. So the full step would be 1, and then you just take the QP solution as the next iterate. That would be the simplest thing, and the same similar for multipliers, but here we don't need the multipliers. And I should say that this whole thing gets I forgot one thing. First, get new Hessian approximation. And of course, this could be a step that's containing a lot of details, bk plus 1, and then you loop. And this new Hessian approximation you couldn't get by updates. That is one way. Then you need to somehow make these linearizations that keep some memory, as I discussed before. You could also use a Gauss-Newton Hessian. In this case, the Hessian just depends on the primal variable w. That's particularly easy. And if you do a full step method and a Gauss-Newton method, it's extremely easy. Huh? So the simplest of all variants. Yeah. I just want to outline it. The simplest variant is Gauss-Newton plus full steps. Yeah? And that's the variant that is very successfully used in a lot of embedded applications. And I will outline it only for quadratic objectives, which very often we have. And in this case, you would just say in each iteration, the objective is now f of w is equal to w transpose some matrix b times w, and I think all the rest I could get rid of. Maybe I add a gradient to make it look more general. Yeah? And so what this method, no, I don't do it. Just makes it uglier. So I have as a subproblem, I will just solve this objective function, because if I do the Gauss-Newton approximation, it turns out that after a little bit of algebra, my objective will be unaltered. And then I just have dwk minus plus dg dw wk w minus wk equals 0. And here the same for the equalities. dh dw wk w minus wk smaller and equal to 0. And so you get this. You need actually a wk as an input, and you get out of the solution a wk plus 1 that then you can use as an input to the next one. So that's the cheapest and easiest algorithm that you can imagine in this class. You basically just linearize your constraints because your objective is already quadratic. You don't need to do anything there. And you just solve a QP, and that gives you directly the next guess. So that would be a very simple algorithm. It's not necessarily converging, but we know that it will converge under some circumstances. In particular, if this Hessian, we could also replace it by something slightly bigger in order to ensure that it converges. Coming back to that point here. Okay. I didn't really discuss why SQP methods converge and what happens there, but I want to give you the intuition of them. So what happens in an SQP method, you solve this QP will have an active set. The QP solver will know some solution points, some constraints to be active and some others to be inactive. And so if you start close to a real solution which has this strict complementarity and LICQ and so on, the QP will actually discover the correct active set. So that's a theorem that you can, or that can be proven. So if you're close to the true solution, then you get the right active set. And then actually the inequalities that are active, they are really treated as if they would be equalities. So they remain active from one iteration to the next. And you recover the equality constraint Newton's method, which we had already discussed. And that one, we said, if there is the exact Hessian here, we will have quadratic convergence, and if there's something else which satisfies that condition, then it will at least converge locally. So you see that once you have the right active set, everything would be okay. And now the fact is that SQP methods, you can ensure that they also have a descent property, so they actually decrease the objective, and so they come closer and closer, and at some point they will have discovered the right active set. But okay, that sounds a bit fuzzy. In practice, actually, they usually get the active set quite quickly. So you might have, like after the first 2 or 3 iterations, you might already have the full active set correctly, and then it's converging quickly. So that is what I wanted to say about SQP methods, and I wanted to say also a few words about software implementations. So there is a code SNOpt. That's probably one of the best active set, sorry, not active set, but it's an SQP method. It's unfortunately not open. There is some tools, computational tools, which are actually popular in the field of optimal control, which are called shooting methods. And so some other tools that you cannot, this is also not open source. Moscow 2 is a tool which implements an own tailored SQP method. Arcado is an open source tool, also has an SQP method inside. In Kazadi, there is, I think, Kazadi also implements SNOpt, and it has also some SQP method that's called block SQP, which is not fully mature yet, but you can actually use and call it. And there is some codes I know of called filter SQP. And I surely forgot a lot of important SQP solvers, but there exist many, and basically what you need to implement an SQP method, if you think of it, you need a QP solver and you need derivatives. Derivatives you have now, for example, with Kazadi or with any other tool, so you can get derivatives quite easily nowadays. And QP solvers also, so plug them together and you have an SQP method. Yeah? So that's what we will also at some points do. I should say that there is fminCon, and fminCon in MATLAB is an optimization routine which is in the default form actually based on an SQP method. It might change actually, but for a while there was an SQP method and I think it's still in there, by Szytkowski. So a closed source SQP method. Okay. Other questions regarding SQP? It's fast. So maybe I should directly tell you, Andrea and I decided that you would get an exercise sheet which is this time not having a dynamic system but only optimization. So it could also be in an exercise sheet in a normal optimization class, because we thought that the interior point method, needs to be implemented once so that you get an idea of how it really works. Yeah? So we want you to implement an interior point method. And if you like, you can also implement an SQP method, which is like a bonus question here. So to get an idea, using an SQP solver, a QP solver should be relatively easy, but the interior point method, you really do it into the linear algebra level, because these systems, this is the root finding residual, and you need to compute its derivative, put these matrices, construct them, invert them. Inverting you can do with MATLAB, of course, but so it's good to look once into the details of such a method. So here I want to stop the first hour and distribute this sheet, and 3:15 we continue. Okay, so please take the sheet if you don't have it. Okay, so everyone has picked up his or her coffee, and no one is missing. And I would like to continue, and I would suggest that I continue with inequality constraint optimization a bit, where I still wanted to present one more class of method families that you should have heard about, and these are called the active set methods. for active set methods, I hesitate a bit to bring them into this part of the overview, because usually they are actually applied not to NLPs directly, but to QPs or LPs. But the spirit could also be applied to NLPs, so it's actually it's fair to just explain them in the general case. I will only explain them in words. There is not so much formulas I will present here. And the words that I want to use are actually the following. So if you have a guess of the active set, if you would know the active set of an NLP or of any optimization problem, right? If you would know what is the right active set, then you could actually just solve it by a normal root finding problem. Do you agree? So, of course, you don't know the active set, but if you would know it, you would just fix it. You would just say these inequalities are equalities, and I just want to satisfy them with equality. And all the others you throw away and you don't look at them. And then you have a square system of equations with this G tilde, so to say. You can solve it. And maybe I should just say solve. The idea is fix A, but as a guest, right? A guest. And solve. And now what do we solve? You solve f of w subject to g tilde of w being equal to 0, and the g tilde is as before the equality constraints that are augmented with the active constraint. So, and this could be the solution to your problem or not. And if it is the solution, then it will satisfy the KKT conditions. Yeah? For example, all the multipliers for the inequalities, which is the second part of these equality constraints, they should be now positive. And if they are not, then you have a problem. So then it's not a KKT point. So you will actually check the KKT conditions. And if they are not satisfied, modify, then you stop with success. So then you are ready, if you have a point, or modify A, if necessary. And so, of course, there are also many ways necessary. So there are many ways how to modify this A, and I want not to present the details of active set methods. I just wanted to say that in the case that you have a QP, this f is a quadratic function, this g is a linear function, you know that this thing is just one linear system solve. So it's very quick. There's no Newton method, nothing. And so you can actually very quickly compute the solution of this thing, check the KKT conditions, and then you modify this A if necessary. And so there are many variants of active set methods, I said. And one active set method that is particularly easy to visualize and to imagine, and that's these are called the primal active set methods. They go as follows for QPs. I think I want to visualize them just as a picture. So you have a quadratic objective. You have some constraints. This is not. Yeah, this is not a good picture. Maybe I put more constraints. Sorry, I put even more constraints. So here is another constraint. And you start with a feasible point. Yeah, that means this is excluded because all these are, so this constraint is redundant. I don't need it. Yeah? This one is nearly redundant, but I need it here at this little point. So the solution of that QP would be at this point, right? So that's the minimum point in the feasible set. This is omega. We could have three active constraints, this, or of course two at the same time. And what an active set method does, it actually starts to somewhere on a feasible point, and I make it difficult for the algorithm, so I let it start at this point with this guess of the feasible set. So it will now solve a QP which is constrained to this surface, and it doesn't know about any of the other constraints. And because these are the quadratic level sets, it will land at some point here, which is infeasible. It's very easy to check that, or to compute the largest step that is still in the feasible domain, and it will stop here. And at that moment, it will detect actually that there's another constraint that is somehow blocking you, and this constraint will be added. And then you have two constraints, and then it will give you this solution here. Because two constraints in two dimensions, they constrain you, you will land here. But you will not realize that one of the multipliers is negative, and so it's actually the one corresponding to this constraint, and then you drop it. And then you will move only on this interface, and that will lead you to this point, and then it's a blocking constraint again, and so you have the same story. And after two more iterations, you will be on this line. And then you will find this solution, and at that moment you check the KKT conditions and you will be done. So you see that you have a finite number of linear system solves, and afterwards you have solved your system. This was quick and dirty. I don't assume that you are able to reprogram it, but it gives you the idea. So it actually moves on lines, finds points, changes the active set, and at the end it finds a solution. And unfortunately, these methods, and that's also the reason why people were very unhappy even about linear optimization, where a similar method exists. In a high-dimensional space, so imagine you have a cube, right? In 2 dimensions it has 8 corners. In 3 dimensions it has already 16 corners, right? No, sorry, it has 4 corners in 2 and 8 in 3, and then it gets a factor of 2 every dimension you add. So if you have a hypercube in many dimensions, you see that in principle there are so many corners that you can visit in such an algorithm that it grows actually exponentially in the dimension of your set. And there were people that could construct examples where nearly every active set strategy would at the end visit and would go, so to say, through all corners of this problem. And this is, of course, a very bad behavior, which is actually not polynomial in the problem dimension. And so this was a famous paper by Klee and Minty. Counterexample. So this is something that lets no polynomial runtime guarantee for these methods. That paper by Klee and Minty came before the interior point methods, so that's why the interior point methods were so popular, because they until then one thought that only this class of active set methods would exist. Yeah. So I add the remark possible for NLP. So you can imagine this for NLP, but much more popular, and I know of nearly no NLP solver which is based on an active set method on the outer level, but more popular for QP and LP. And in the case of LP, you call it the simplex method. And for LPs, it's still one of the most competitive methods together with interior point methods. So most solvers implement both interior point and simplex method, and you test which is faster on your instance. Or you can test. Okay, so that's all I wanted to say about active set methods. It's extremely short, I admit this, but you should have heard the name. Yeah? So active set methods are a kind of discrete testing until you have found the right active set. Maybe I should give you one little remark, just to give you this little remark. You could, of course, do the following, and this is a very naive active set strategy. You just say, how many possible sets alpha exist? Alpha is a subset of, A is a subset of all the indices n, h, right? So each of them could be contained or not. So it's actually, the number of all sets A that you can have is 2 to the power of n h. So a constraint can be active or not active. So there's only 2 to the power of n h possible active sets. So in principle, you could just, if you have 3 constraints, you can construct all 8 possible active sets, solve each problem with the Newton's method, and then look if one of them solves the problem. And then you should be happy. It could actually happen that 2 or 3 solve it, because you are in nonlinear optimization, right? So there could be different local minima. But each of them you can check with the KKT conditions, and usually they give nothing, and it's very useless to try them all. And this active set strategies try to test them in a slightly more intelligent way. And one of them I tried to sketch here. Okay. Of course, once you have 10 or 20 or 10,000 inequalities, you don't want to enumerate them, but still active set strategies can be useful in that context. And as a rule of thumb, if you want warm starting, so these are good at warm starting. So that's why you want to use them, and on the other hand, they are bad when you have millions of constraints, because then you might need to visit all of these possible active sets, or many of the active sets, and it can get very, very slow. Yes?
Wouldn't this method also be possible to work in parallel?
Yes, this one that I just explained, you could make work in parallel, of course, but unfortunately with exponential number of problems, it doesn't help you much. I mean, once you have 20 inequalities, it's 2 to the 20. Yeah. It's, you're right. So whenever you get large numbers, you can easily do things in parallel, but once the numbers get so quickly, so large, parallel doesn't help either. But it's a good remark, yeah. Okay, if there are no other remarks on this extremely superficial overview, then I want to go on with rehearsing concepts from optimization and finishing by mentioning globalization strategies. So also that you know what is happening inside these algorithms. Globalization strategies, and I mentioned already in the Newton's context that we can do a kind of line search to make steps shorter, and we can have a criterion for descent that you remember, recall Armillo line search. Huh? So that's what we had already in chapter 2. And I just wanted to tell you that this is, of course, this idea of globalization can be generalized to inequality and equality constraint optimization problems. And there is, of course, a full variety of possible concepts. And the main two dividing lines, or the two things that distinguish the different globalization strategies, are two things. And one is that you need to somehow decide what does it mean to be better, because most of these algorithms want to ensure progress in some way. So you need to measure progress, and I gave it a section, 4.1. So you need to measure progress. And the other thing, which I put on this blackboard to save space, is, well, maybe I don't, because then the camera needs to move, right? 4.2. The other thing is you want to ensure progress. So these are two different things. One is, first you need to know what is good and what is bad. When is a step actually a better point than before? But then the next thing is, if it's not a better point, what do you do then? So how do you ensure that you really make progress? So if you think of the Armillo line search, you measure the progress. In that case, we had this square of the residual. Yeah? So here we had just V of Z being R of Z squared. You remember that? I think I put a 1/2 here. That was measuring progress. And then to ensure progress, we would make the step shorter if necessary. And so these things are not the only options. So for measuring progress, we are already familiar, so to say, with this concept of a merit function. It's like what we had here. But there is also another concept that's called filter in optimization. Yeah, so merit functions and filters. And on the ensuring progress side, there is also two or more, of course, but most popular are line search as one thing. And the other concept here are trust region methods. So I want you just to be sensitive about these differences. So a merit function is something that should be small for the optimum, and smallest actually for the optimal point. And so for a merit function in optimization, you need to somehow not only have the objective. I mean, what is an objective? The objective is something that is definitely something you want to have small, but you also don't want your constraints to be violated. And so one way, and this is a very quick way to note it, is that you introduce a penalty sigma, and you take the one norm, or it could be another norm, but it should be a norm at least, and not a squared norm or something, of the constraint function. So this is what you definitely want to be 0, and the one norm is something that's actually steep, right? Or any norm is steep at the origin, so it's really steep. And you add also, and I give another penalty, no, I have the same penalty parameter even, plus the norm, and now I do it for the positive part of my functions h. So this is a very shorthand notation. So if an h function is positive, it is a violated constraint, so I will penalize it. So I will count it. If it's negative, I will not count it. So this is actually a quick way to depict something that is 0 for negative values and then positive values count. Okay, so that's actually, so a ramp function basically applied on h. So you see that when your point is feasible, then this is 0 and this is negative, so this will not count. Negative or 0, so both of these terms are 0, and then it's just the objective function. But once you get a violated constraint, these terms will kick in, and they will make it expensive to violate constraints. And this whole function is sometimes called TW, so the L1 merit function. And the theory goes that if you make the sigma big enough, actually bigger than the multipliers corresponding to all these constraints, then you can really be sure that at a local minimum of your problem, also you have a local minimum of this T1 function. And so going just down with T1 all the time in all iterates is a good measure for progress. Yeah. So you need sigma large enough. And now you see already that this sigma is a nasty parameter. It's possibly, I mean, depending on how high your curvature, your slope of the f is, you might need quite some sigma, and then the sigma will also make your this is, by the way, a non-smooth function, so it's also nasty. So you will have some disadvantages of this measure of progress. And so there are some other ways. I mean, I should also say, which I didn't mention, augmented Lagrangian is another way. Just so that you've heard about it. But what I wanted to introduce are filters as a quite popular way. And filters are working differently. They actually keep track of all the values of f and also of the constraint violations that you have visited already. I mean, every iterate in a Newton type method gives you a pair of an f and a constraint violation. And then filters say, I give it up. I don't want to weigh the objective with the constraints, because constraints in principle need to be infinitely highly weighted, so I cannot compare them to objectives, so no use to add them up. And the filter actually tries to keep, so to say, in a landscape of f and norm of the constraint violations and h plus. So small is good, right? So the optimum will be where this thing is 0 and the objective is small. So this could be the optimal point. But during your iterates, you might have found some points that are here, like better objectives, but unfortunately violated constraints. Some other points that are here, maybe. So these could be the iterates that you have found already. And you say an iterate is only better if it is, so to say, either if it's not dominated by any of the previous points, and dominated means that if I now want to test if this is a good point, then you say, no, this is bullshit. It's not as good as this one. It has a worse objective. It has a worse constraint. Yeah, so you will not accept it. On the other hand, if the point is here, for example, you can say, yeah, okay, it has a, it's not dominated by any other point. So it is not, it's either better on the objective or it's better on the constraint, but it's not worse on both. Yeah? So that's what a filter does. Just a very rough idea. That was quick, and I promised to be quick. And so the other thing is, so now you have a measure when you want to accept a point. In a merit function, if you want to, if you are better, if this merit function is smaller, then you are better. In a filter, if it's giving, so to say, it's a non-dominated point. But still, there's the second question is, if you don't satisfy this kind of progress criterion, you need to ensure progress. And so one way to ensure progress, that is also the one that we did already, is that you just say, I somehow have my linearization, so maybe if I make my steps smaller, I can ensure progress. And usually, of course, the measure of progress and the way to ensure progress are intertwined, because you need to make sure that if you make some parameter small enough, you actually really make progress. And for line search methods, under many circumstances, you can combine them, for example, quite well with either filters or with merit functions. But there's another way. Line search, I mean, is clear. We did that already. So line search means use damping of the Newton step, yeah? Or Newton type step. So you basically do something like this. WK plus 1 is equal to WK plus, as I said, alpha times WK QP, for example, minus WK. Now for interior point methods, you could also do it. And for trust region, it's a bit more complicated. What you do there is you will actually modify the problem. And for example, the QP subproblem in an SQP method, modify QP subproblem. So it's very much combined to the QP interpretation of Newton's method by a constraint. Maybe I add that. So by an additional constraint, which says basically that the step W minus WK, so the distance, in some norm should be smaller than some radius, which I could call, sometimes it's called delta, just with this symbol. So you basically, if you think of it, if it would be a 2 norm, then it would be just a circular constraint and the radius is delta around your old point, and you just say, I don't want to move further away from it rather than this radius delta, and you reduce delta if necessary. And you reduce it and you resolve your quadratic subproblem in order to get a hopefully better point that then accepts your measure of progress. So these would be the 2 dimensions of globalization strategies. Very quick, but maybe one high-level remark, if you just to be sure, when we say globalization and optimization, we shouldn't confuse it with global optimization, right? So when we say globalization, it's just about finding a local minimum with a Newton-type algorithm. And global convergence means you started somewhere and it will somehow go to the vicinity of your solution. Or to a local solution, sorry. Maybe another remark, in practice and also in optimal control practice, sometimes all these methods fail and people refer to something that we call homotopy strategies. So you actually solve a simple problem first, you modify it a bit and then solve it again, and you modify it a bit and solve it again, and you always keep track of your best solution until now. And that sometimes is the only way how to make some problems work. Yeah? So you sometimes combine a solver like IPOpt or an SQP-based solver together with a higher level thinking where you just solve your problem or a similar problem, and then you modify your problem until it is really the problem that you wanted to solve. A bit like sometimes I program like that. So you do something like a simple thing first, so something that works, and then while it works, you modify your code until everything that you wanted to add is added. So you modify by pieces, and all the time you keep track of local minima. So that's another way to globalize, but it's not really called globalization because it's not a method, it's just something that people do in practice. I think this is a good moment to stop, and what I want to do next time, that is on Wednesday, I want to confront you with the topic of derivative generation, which we used already, but I want to explain a few details of what's happening inside Casadi so that we know how derivatives are computed. Okay? Thank you very much.